9.3. Last content lecture for the term. So next week's all exam reviewing, or like just chatting about the exam and stuff. This is the last topic on data structures and algorithms, but particularly this one's a data structures one, and this is about tries. Tries are a type of tree structure that focus on storing a large set of strings efficiently. Because if I just said to you, here's a million words, right? Think of it like assignment 1, how you had all these different words and stuff. It's like, but there wasn't even that many in assignment 1. If I asked you to store a million words, or every single word that appears in every single whatever, you could store it in a hash table, right? But that would get really big. If you had like a million words and collisions and all that kind of stuff, that could get really crazy. So we need a more efficient way to store like words. That's kind of where this topic has the most like relevancy. And we store these things in a data structure referred to as a trie. Spelt like T-R-I-E-S, but you just say it like the word try, like I'm going to try to give this lecture today. So tries are data structures that represent strings, sets of strings, that support OL lookup, where L is the length of a string. So what that means is if you want to store a whole bunch of strings, headphones, money. I'm just looking at things on my desk. It's like water, tape, mask, Panadol, remote, koala. Don't ask about that one. If you want to store all of these in some kind of data structure, if you store these in a list, your space is pretty low, right? Like you only have to store 8 elements, but your lookup time is going to be on, where n's the number of items. Now that's a problem because the biggest word in the English dictionary, like not the biggest, but like a big word in the English dictionary is like 20 characters maybe. It's quite large, maybe 15. But if you have a million of those words, you don't want your lookup to be like on. If you have a million 15-letter words, you don't want to have a million time lookup. So that's storing it in a list or a linked list or something, an array. Maybe you could do some kind of binary search on an array. The other way you could do it is store it in a hash table, because we know that hash tables have O1 lookup, right? Okay, but hash tables aren't perfect. It's probably better to use a hash table than this, but one of the problems with the hash tables is that you need to pre-allocate a whole bunch of space, and once you start getting collisions, you run into some problems. And we don't want to run into problems. So a trie structure tries to keep the lookup and insertion complexity to OL. So instead of it being ON, it's actually kind of like this. It's over this way. It's OL. So it's actually the length of the string that's the complexity of it. And the way we do that is by trying to store items in a structure like this. It's like a 2, 3, 4 tree. It's like a B tree in the sense that each node can have multiple children. It's not like a binary tree where it's just like left and right, but each node can have multiple children. And the idea is that every single word kind of exists down a particular line. So it's like ace here, for instance. We start at the root and we go A-C-E, and then we have aces, A-C-E-S, and then we have ape, A-P-E, A-P-E, apes, A-P-E-S, and then we have app, A-P-P, apple, A-P-P-L-E, apply, A-P-P-L-Y, and so forth, etc. So, so you're actually kind of layering things on top of each other, right? Like in terms of we stored aces with just like A-C-E, and then we stored ace with just A-C-E, and then we stored aces with A-C-E-S. So we kind of like had an overlap there where we reused 3 of those characters. So that's how I kind of think about it, is like you're essentially trying to layer things on top of each other to avoid redundant storage. And you're using like a tree-like structure like this. The depth of the trie, like if you're talking about tree depth, then the tree depth is just the longest word, right? Because the longest word is going to create the longest path from the root down to the leaf. So here the tree depth will be the longest word, which is apply, which is 5. So it's like 0, 1, 2, 3, 4, 5. So that's why the tree depth is 5. Now, you could use a trie I'll come back to that question. You could use a trie to store things like this. Now, not every word in this array up here is being stored in the trie, just some of them. But you can see that things like C here, SEE, are stored SEE like that, you know? And you can see things like A here. Is A stored in this? No, it's not. Bear, for instance, BEAR, is like stored here. So it's quite like conceptually, I think this is one of the easier data structures we like need to talk about. So it's, yeah, you just literally take the words out and you like build it down. And if the first elements are there, like if you're trying to say add bears, like the plural of bear, then you just come here and you say, oh, there's already a B, there's already an E, there's already an A, there's already an R. So I'm just going to add another node down here for like S. Would this have helped in assignment 1? I don't know. It's hard in my brain because I didn't do that assignment, so I'm sure you guys will figure out whether it would have been helpful or not, though. Maybe? Oh. I guess so. I don't know. I'm not going to comment. I have to think about it. Someone will know, though. So, yeah, that's how we conceptualize tries. Pretty simple structure. Before we get into it, what are some problems with this? Like, someone tell me, what are some problems you foresee with this approach? Because it seems kind of too good to be true, doesn't it, in a way? Like, you look at it and you're like, oh, wow, okay, well, that's really fast lookup. We basically have the benefits of binary tree, except it doesn't have to be numerical. We're actually storing whole words in there and multiple words. In theory, you could store hundreds of words with only, like, you could store 1,000 words with potentially only 50, 60 different characters needed, or something like that. So what are some downsides of this structure? Or some challenges you might think? Like, you're mature enough in this course to think about implementing this, right? Like, you've done trees and graphs, and like, a bunch of you are going to be like, looking at this and thinking about how you might actually code it. D. Aurora says, you don't know if the singular is in the trie with plurals, etc. Sure. So how we get around that is, you'll notice, and hopefully I'm understanding you correctly here, but with a trie, what we do is every time that a word finishes, we mark the last letter of that word with a red cell. So you'll see on this conceptualized trie here that we have things like ACES and ACE. What the red means is that this is actually where a word terminates. So when we see A, we're like, okay, A, first letter. Is that a word? Is it red? No, it's not a word. C, AC. Is that a word? Well, it's not red, so no. And then it's like ACE, that's red, so we know that ace is a word. And then when we look at S here, now we know that ACES is a word. So the red tells us that it's the end of a word. So that's kind of how we have these things overlap with each other, is we basically do like a true or false stamp flag on particular nodes to say this denotes the end of the word. And because like a normal tree, every node only has one parent, it's completely clear as to what that word is. Like, if you say it ends here, then you know exactly what characters before that came from. So really interesting structure. Gorb says single letters could have tons of children, not in the English language, but maybe other items. Yes, so one of the challenges to get around with this is that, how do you implement it? So like, that's what we're going to talk about now. So the trie structure, if we look at this, each node in a trie contains the character that it contains, right? Like a letter. It contains the children, children like this. It contains a boolean as to whether it's finished or not, and then it contains an item data. I'm not sure what that is, actually. I'm suddenly confused what that is. Oh, data for application. Sure, sorry. Yeah, it could contain other data for your application. So again, assuming I haven't missed something, like if you were to try and use this for assignment 1, for instance, then if you're trying to store a whole bunch of word frequencies, like, it's not just enough to store a trie, because a trie by itself is just a set of words. But if you have a piece of data, say an integer on each node, then potentially you can store the frequency. So if it is the finish node, if it does denote a full word, the end of a word, then you could keep track of the frequency it occurs in, which could be super efficient. So that's all good. What are some problems with this structure though? Well, one of the problems with this structure that I don't know if is mentioned, where do we mention it? Maybe it's not mentioned in the slides, but one of the problems with this structure is that every single node here has exactly 26 pointers, and a pointer on a modern computer is 8 bytes. So while you look at this structure and you think, oh, that's super efficient because we can have a lot of overlapping, the problem is that this particular model here, just for lowercase words, just for 26 lowercase characters, each node is going to be 1 byte, 26, like we could figure this out pretty quick, right? It's going to be 1 byte for the char. It's going to be then 8 times 26. Pointers 8 bytes times 26, so it's 208 plus that char, plus a bool, which is a byte, plus an item, which let's say it's an integer. So a standard integer is 4 bytes on the computer, right? So it's 214 bytes just to store that. That can be really... That's quite a heavy node, right? That's a really heavy node. So when you look at a structure like, say, this one here, sorry, I jumped it around a bit. You look at something like this and you say, oh, this is not too bad, but it's like, how many nodes are there? Like, we haven't even counted them all either, because each one of these would have their own children. So it's like, you have the root, you have like A, which is 214 or whatever. Actually, I think we can just count how many exist, because the children are implicit. It's like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's like, 18. That's like that many bytes, nearly 4,000 bytes. And it's like, well, how much is a char? Right? A char is 1 byte. How many words are we storing here? 1, 2, 3, 1, 2, 3, 4. We're storing like 3, 7, 10, 14, 17, 22, 27, 31, 35, 45, 49, I think. So it's like we're storing 49 characters. So do you know what I mean? Like, if you stored this in a list, imagine storing this in a list, in an array of pointers to an array, like an array of strings, you're going to actually be storing a lot less bytes. So immediately you can see some space considerations in this kind of approach. Remember, this is a specific implementation. So just to store these characters here in an array would probably be, I think I said 49, plus they all need a null terminator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they all need a null terminator. So that's 61 bytes for all the characters and the null terminator. And then let's say you put them in an array and you've got your 12 items here. An array of pointers, right? Sorry if I'm getting too mathsy for you. It's like you might have an array with like 12 items in it that all point to strings. Right? So then these all point to strings which also have a null terminator at the end. So you think about what the size of all these things are, right? It's the size of the string, the null terminator, but then also every one of these in the array is a pointer. So now you're dealing with 61, which like that means that all of these are going to be 61 bytes all up. And then your array, which is 12 items times 8 for pointers, is 96 bytes. So just storing these strings in an array of strings is going to be 157 bytes, and storing it based on the implementation we just provided on the slides is going to be that. So therefore, if I divide those, you get those pretty quickly. It's like one uses 25 times more storage. That's not to say it's worse. I'm not trying to sell you that tries are bad, because they're faster too, right? Like we've said that at the start. Iterating through a list of strings is really slow. But I'm simply trying to demonstrate here that again, there's nothing particularly perfect in this world. Everything has a use case, otherwise we wouldn't teach anything that was literally never used. So it's like tries are really a decision to try and make your space complexity, this implementation specifically, has pretty big space costs, but massive time improvements, right? So yes, we'll come back to this because there's some alternative data structures we'll talk about. There was a question. Yeah, Gorb says, why not do a linked list? A linked list, you'd actually have to look through every child, so a linked list would save you time, but the problem is that, the linked list would save you space because you're not storing 26 pointers, you're only storing like as many as you need, though the problem is it would make lookup really slow. It would make it, I think a linked list essentially turns this into a, I don't know, let's think about that in a sec. Searching makes sense in a try. If someone says, do you have the word early in your try, will you go, let's start at the root, E-A-R-L-Y. Why is it a finish node? Because it's red, so it's definitely a word. So yes, I do have it in. That only took me 5 steps. That's OL, where L's the length of the string. It doesn't matter how many words are in this try, it's still OL. That's a real powerful part of this thing. Try insertion is pretty easy. You start at the root. If the try is empty, then you create a new try. If the try is not empty, as if something's already there, then you basically do a recursive insert. It's like inserting into a binary tree. It's quite literally the same. You start at the top. You say, is this where I finish? If not, you just keep going down. As you can see here, it's recursive in the sense that we check if m is 0, where m is, what's m in this case? I think my brain's melting. What is m, the length of the... Maybe that's poorly specified. I think m might be the length of the word, like the number of characters remaining, potentially. I'm not too sure. The point is that you know the word you want to insert, right? Like if you're trying to insert a word, you insert things like, how would you put it? Yeah, you want to insert things like empty. So what you do is you look at E, you find the E one, you go down, and you just keep recursively going through the try until you get to the end of the word, and then you try and insert it there, basically. Like, so inserting is... Do I have a slide for inserting? No, I don't have a slide for inserting. That's okay, because if you want to insert something like cat, you just come down here, and there's a C. But there, so you then look at the A child, but there's no A, so you create a new node, and then you look at the T child, but there's nothing there, so you create a new node. So it's inserting is just going down the tree and creating new nodes as you go. We don't really talk about deletion in these slides. It's not something we're really interested in these cases. But deleting is also kind of it's not easy, but deleting makes sense because it's like if I said to you, can you delete apes? You would come down here and you would delete the S because the S is at the end. And if I said, could you delete ape, APE, you would just come down here and you would unfinish the E because you can't just delete the E because it's used by another word. So generally speaking, it's like deleting is either cutting leaves off, or if you're trying to get rid of things that are before the leaf, you just unfinish them so that they're still used by other people. Now, the space complexity we've said is the sum of the lengths of all strings. Worst case, sorry, I was just looking. So yeah, space complexity ON, where n is the length of all the strings. That makes sense because if you have like 10 strings, they have 20 characters each. It's a terrible example. The worst case with a try is that you don't get a lot of overlap for some reason. An example would be what happens if you try and insert A, or like seal, and then you try and insert ace, and then you try and insert pace, and then you try and insert space. Now a standard try is going to insert this in a pretty ugly way. It's going to go like C-E-I-L, and then it sees ace, so it says, oh, the first character is A, so then it'll do this, and then it'll see pace, and it'll say the first character is P, and you'll end up with this, and then space, you'll end up with that. So this is actually how a try would look, and in this case, the space complexity is one node for every character, so it scales proportionally in the worst case to the number of characters that exist. But if I inserted this, actually no, this would still be bad if I inserted it the other way. There needs to be commonality with the start of the word. That's one big thing here. So you don't actually get a lot of benefit in cases like this. You don't get any benefit, in fact. Do you get any benefit compared to a list? I mean, I guess you get some benefit in some kind of like lookup structure. Insertion complexity is OM, where M is the length of the key string. That makes sense because you can look up directly where to go. And then search complexity is also OM. M and L are used interchangeably here. Like, this is something you just have to get used to. Just because we call it OL, it doesn't mean if you Google it, you're going to see OL. It's the length of the string. It's the big O notation is the length of the complexity is the length of the string. You can call it M, you can call it L, whatever, but it's the length of the string. Now, as we said before, the representation we've just talked about is space inefficient. Each node has 26 possible children. So even with very many strings, you're still going to have tons and tons of empty array. In fact, a standard trie like the one we've mentioned before is predominantly going to be made up of empty space. Like null pointers, which isn't very good. And if we start doing things like adding all ASCII characters or like all alphanumeric, and we get into 66 characters or 62 characters or whatever, suddenly the branching factor gets massive. And like as Gordon just said, do people use tries for Unicode too? So like I suspect that tries would never be used for Unicode text for that reason. For people who don't know what Unicode is like a much bigger character space than ASCII. So it's like, that's why like if you have like gedit here, right? And let's say I open Firefox and I take something like I Google the poo emoji, and I copy the poo emoji from Wikipedia, and I try and paste it in gedit. I don't know what happens. Does it work? Sort of. So like really simple text editors, even like Terminal, generally will operate with like ASCII or something, right? In the sense that if I try and paste this in here, I'm just going to get a... Oh my god, it even works there now. Who knows? It's hard to keep up. So ASCII is kind of like a really simple character space. It's got those 256 characters. But most modern text editors, web browsers and stuff can handle emojis, right? Which are actual characters. So can you put them in URLs? You can't, right? So a URL is like a URL is probably ASCII or something like that. Whereas if I go to WebCMS3 and I try and create a notice here, like most modern things are... no, I'm copying that. God, nothing's working for me. It's probably because I copied it out of VLab. The point is that most text editors now, like, this is considered a character. Just like A and 1 and 2, these are all characters now. So Gordon's question around, would people use tries for Unicode characters? Probably not, because, like, I don't know, Unicode character set. How big is it? Unicode UTF-16 character set. I mean, I guess 16-bit. What does that mean? Holding a million different characters. Could you imagine if every node in your trie had a million pointers? That'd be 8 million bytes. That'd be like 8 megabytes? 8 megabytes per node or something? I mean, that's a very naive solution. In reality, you'd never do that, of course. Caleb says, Tangent, there was a really cool talk at B-Sides Canberra this year about where emojis can be accepted. That sounds like a fun talk. You should post that on the forum if you... Unless it was recorded? I don't know what happened to B-Sides this year or whether it was recorded. Yeah, so another way that we can do that is instead of sticking with a branching factor of 26, we can actually collapse our trie to like a more binary search tree-like structure, so that we could either collapse them into having like, 8 or 4 or 2 branches instead of 26. And an example of that is if we take a trie like the one we have on the left here, which has a branching factor of, say, potentially 26, we could reduce it to something like we have on the right, where it's basically a binary tree. So where everything on the... Yeah, where you just have to check 2 nodes each time. Now, naturally, this one's going to be slower because the longest path, like all trees, complexity is generally the longest path through the tree. It's A, B, E, I, O, D, right? That's 6. Whereas here it's just BID. So the actual, now it's going to take twice as long to navigate through this in the worst case. It's not linear like that. It's probably going to be a non-linear relationship. But it saves space because we're not storing redundant nodes. In fact, each node is now only storing, like, say, left and right. So we're kind of treating it like a binary search tree. Trent says, how can you extract the actual words from this? Well, my guess is, I haven't worked with these directly, but if you said I want to insert a word like able, A-B-L-E, you'd come down here and you'd probably look at the left and the right node, and you'd look at if one of those is B, right? Because doing 2 checks is pretty quick. So I look at if one of those is B, I look at that, I get B, and then I look at if one of those 2 children is L, and it's not L, and not sure what you do there. You probably have to do some restructuring. Maybe. I'm not sure. But again, this is by the way, this is just a nugget. This is like a that's why I don't know, because I haven't really dealt with it much. Is like you can store it different ways. I mean, this is just to be clear before let's finish talking about it, but it's not necessarily like you have a try like this and then you're like, oh, now we have a BST and there's nothing in between. A big point of what we're referring to here with the bottom stuff is that you could potentially break your tree into having a smaller branching factor like 16 or 8 or something like that. D. Aurora says, what happens if you make your arrays resizable? Okay, so what happens if, like, your root in a normal try has like just 3 items in the array and then you make it resizable? So if you made your array resizable, that would reduce space, but you'd run into 2 problems. The first problem is that you'd have to resize it potentially, which is costly. The second one, which is probably even more important, is that a lot of the efficiency gains you get from a try is that if someone says, you know, I have character B, C, D, you know that B is index 1, and you know that C is index 2, and you know that D is index 3. So looking up a word in a normal try is really quick, because someone says like M, and you're like, well, I know M, it's the index 11 character or something. So you just like look straight to that array element. If your arrays were dynamically sized, you'd have to put a lot of thought into it to not lose that, because if you just had 3 array elements, the only way to check if it's the right node would be to look through them. So yes, that is a totally valid approach to have smaller arrays, but it just costs you more time. You know, like all things in computing nearly, it's like you want to save space, you're going to have to spend more time. You want to save time, you're going to have to use more space. That's one of the fairly fundamental rule. Some good questions about binary search tree nodes, though. I don't know. You've actually really challenged my thinking on this, because they seem simpler in my head than now I'm realizing it. I'm not sure if there are constraints on this, or if there's restructuring that happens, or if there's something else, because I guess it's right. How do you store, like, what happens if you have A, B, A, C, A, D, A, E? How does that go? I feel like there might be some details missing from these slides. I mean, this is a non-accessible thing, by the way. Like, generally anything I don't know much about is non-accessible by that very nature, so I don't know. I'll try and go dig up some more info on this, but this is not something that you would need to stress about for any assignment or exam related thing. The main point here being is that a try doesn't have to have a branching factor of 26. It could have a branching factor of 128. It could have a branching factor of 16. The concept of a try is storing words overlapping each other. That's kind of the most basic concept of it generally. Oh no, I see now. Sorry, I've totally just my brain has just melted on this front. Forgive me. It just clicked again. So these aren't both children here. That's probably why I was confusing myself before. The left one, like a binary search tree structure, the left one are the children, and the right one is the siblings, in the sense that you can actually take this diagram. I was wondering why I understood this the other day. I was like, you didn't put this in the slide and just not make sense of it. in this diagram in the literal sense that like these are all the next possibility of letters, and then these are all the next possibility of letters. So the grey is actually what joins them together here, like that. Yeah, thank you. I think I need to give credit to Hamish for that, because Hamish's comment just jogged my memory. I wasn't looking at the colors. So yeah, the idea here is that like you say root, and then you say, okay, well the next character is A or B or D, and then if you're like, so it's like, let's say you're looking up a word like big, for instance. You're like, okay, root A, let's check B. All right, we found B, so we're going to go down. Let's check if there's an I. It's not that one. Is it this one? Yes, it is. And then we check down and we're like, is there a G? No. Is there anything left? No, there's not. So we have to insert a G. So in this case here, there'd be a grey arrow here to the G, like that. That's how that would work. So the grey arrow, like one of the things horizontally is like the how would you put it? Like the other candidates for that next value in the list, and the one below it is like the next character in the word. Hamish says this seems like a linked list try, not a BST. Well, I mean a BST is a linked list structure anyway. So the point is that this structure means that you're only storing nodes that you use. So the space complexity of this would be way down. But as we've just seen, and as I said before, in this case, we've had to deal with like a total of 6 steps to look for the word big, right? And yes, that's why we call it a BST structure, because it pretty much just has the same properties of a BST. It's like it's exactly the same as a BST structurally. It's just that you don't have a sense of left and right. That's where I got confused before. I'm sorry about that again. It doesn't have a sense of left and right. It just has a sense of like child or other possibility for this character, like next character or alternate character to the side. And that's also why it's like drawn all weird, like, because the horizontal lines, the grey ones, are like these are the other possibilities to choose. So more space efficient, slower to go through as you'd expect. And then the other way of thinking about this is by potentially doing compressed trees, which is where you take a try, but you notice that there's like a whole string of words in a row, and then like and none of them are terminals, for instance. Like say T and O, like T is not a finished word, O is not a finished word or something, so you just condense them into one node. Because otherwise what happens is, because you have to think about how like the branching works, is every single node here, based on the original implementation we had children. So like this one here has 26 branches. This one here has another 24 branches or whatever. This one here has 24 branches. So the idea here is that if you find 2 characters that aren't finished words, then just combine them together. Save yourself all that branching. So like for something like this, for instance, I don't think there's a ton we could do with it here, because that one's quite heavily used, but this is probably a better example. If we take one like this, for instance, the point is when you look at it, you're like, hey, E and A aren't finished words. So how about we just like make this one EA, like that. And then we just get rid of this. Because it's like, if there's no words that finish here, then they're all going to be like EA something. So let's just store EA in a node, and then we can stop all those branchings and checkings and stuff. And you could do the same thing here for like TH. You could compress this and still make it a finished node. Like you could put a T here like that and get rid of that. You could put an S here and get rid of that. You could put a P. I don't think you can do it too well there. But you get my point. You can kind of find spots where you're like, it's inevitable. Like, if it makes it past the P, it's either an LY or it's not, because L's not finishy. So you can kind of collapse linear strings of things together to save space. Again, like all these things, there are trade-offs. The benefit of this is that you save space. You don't really cost yourself any more time, I don't think, from what I've reasoned with this, because, you know, like STO, if anything, you might even speed it up slightly, but you're not costing yourself more time and you're saving space. So what's the downside? What's the downside of a lot of things that are no slower and save you space? You have to restructure them sometimes, right? Like binary search on an array. Faster doesn't use more memory. Harder to maintain. Same kind of thing here. This is harder to maintain because, as Diorora just said on the chat, you have to split it later potentially. So it's like, it's all well and good when I combine E and A, but what happens if someone tells me later that EA is an actual word? Well, then I have to go and break this out again and make a node and then relink stuff. So the restructuring cost is very huge. And the reason we talk about these different structures, again, is not because you're going to get an exam question on compressed tries, like to build a compressed trie with code. It's because we want you to reason about it. So, it's like, how would you take a trie and speed it up? Assuming that there's no more elements being inserted. That's why the devil's in the details. I'm finishing up in like 1 minute, 2 minutes max. That's why the devil's in the details with these things, because it's like, compressing a trie sounds like a great idea if you're no longer restructuring it, because you'll see space improvements if you're storing it longer term or something like that. This brings us to the end of today. I mean, it's just a different slide of that. This brings us to the end of today. Please pause live or recording and take a photo of this on your phone really quick, give a rating so I can get a sense of it. And thank you for listening to me talk about tries. Really, really fun stuff. That's the end of content for the course. There's nothing more we're going to expect you to learn. I'll send you out a notice tomorrow or Saturday morning about your assignment 1 marks and about some reminders about last labs and last quizzes. But yes, we're coming right to the end now, so sounds good. Thank you, everyone, and I will see you all on Tuesday next week, and we'll talk about exam and stuff. So yeah, have a great weekend. Stay safe. All of that. Stay safe. Stay safe. Stay safe. See you later.